Thanks. It's a pleasure to be here, and thanks for having me. I'm going to talk today about SDSS-4. I'm going to talk a little bit about how SDSS works, what it does, and then I'm going to give a sort of blitzkrieg view of SDSS-4 science. SDSS-4 is the sort of just ending phase of SDSS. We got our last observations last week. And I'm going to talk about our cosmological observations, our observations of the Milky Way, and our observations of nearby galaxies. And it's going to be a lot of information, but I want to get across to you sort of the many different ways we can measure galaxies now. Well, yeah, but the mask, Yuri, keeps my voice at a tolerable level. So SDSS-4 has 70 member institutions. It's a big collaboration, whole bunch of people. Here's a small subset of them from a meeting in Chile a few years ago. It is primarily funded by these institutions. If you look at our funding map, this is the cosmic pie diagram, dark matter causing galaxies to form and dark matter halos, and all the structure we see, dark energy causing the acceleration of the universe, and the atoms, of course, forming stars and galaxies. And our funding model is very similar to this. The DOE provides about 5%. The Sloan Foundation has, over time, always provided about a quarter of the SDSS funds. And in SDSS-4, the majority of the rest, or all, 70% of our funding comes from institutions like yours. And so it's very much a member-driven project. And what do? We take spectra. We take lots and lots of spectra. And we have two telescopes. Both have wide fields of view. And we have these spectroscopic plates, which have these very precisely drilled holes. We plug them with optical fibers, and they go back to optical and infrared spectrographs. And we observe 8 or 9 of these a night. And so we can very rapidly accumulate spectra. Just to get a sense of how this happens, this is our very precise plate drilling operation here. Very, very carefully calibrated instruments. And this is at the University of Washington. And believe it or not, this sort of Willy Wonka looking sort of operation here is drilling these holes at about 10 microns precision. And it's been doing that since about the mid-90s, 25 years. And those plates, once they're drilled, they get shipped to the observatories. This is Apache Point Observatory in New Mexico. You can see Connie Rockesy in your trademark sweatshirt right there. This is the telescope, the Sloan Foundation telescope that all of this stuff happens on. And then we have a southern observatory as well at Las Campanas. We use the DuPont telescope, which is out at the end of the ridge here. And not coincidentally, is a very similar telescope to the Sloan Foundation telescope. And so at each of those observatories, these plates arrive. And then during the day, they're plugged by hand with these optical fibers. And each of these optical fibers then corresponds to an object in the focal plane. And brings its light back to the spectrographs. And we have some very clever mechanisms for rapidly changing out these plates in the middle of the night that the observers use, so we can do that efficiently. It takes about 20 minutes to go from one plate to the next plate in the observations, 20 minutes of dead time. So those pictures, these pictures are from Apache Point. But one of the big things we did in SDSS-4 was build out new infrastructure at the Las Campanas site. And we've been operating there we operated there for almost 4 years, since early 2017. And so we built a whole bunch of fiber infrastructure there, a new spectrograph that lives in the basement. And we work closely with a set of 8 Chilean institutions to actually staff this in terms of engineering and observers. And these are these are actually some of the early observers. Ivan's now a faculty member at a Chilean university, and Carla actually works at Magellan now. So we had a whole generation of astronomers in Chile come through this team, and it's been a really amazing group of people. So all of this stuff is there to get spectra. I just want to remind you of how many spectra these are. So for example, when EBOS was observing, it was getting 1,000 spectra simultaneously. So here's 1, 2, 3, 4. This is 20 spectra, and so this is only a small part of one plate. And so I can put that up in the corner. And so this is like 1,000 spectra from that same plate, which we observed in 2012. And so this is a lot of data. We get a lot of spectra from this operation. It's a lot to absorb. So when we're done with each of these plates, we're done observing those objects in that location of sky. So the plate's kind of useless after that. So for the majority of SDSS's history, we took those plates and we sold them for aluminum scrap. They're big pieces of aluminum. You can get $5 for them. Awesome. But we decided in 2014 that maybe there were better uses of that aluminum. And so we have now a program where our partner universities work with their local high school teachers, bring in teachers to train them, give them educational materials, and for a curriculum to do a unit in astronomy in, say, a high school class or middle school class, and bring back with them a plate that then they have in their classroom, and some of the activities are geared towards that specific location on the sky. And so this is a really wonderful program. We've delivered a few hundred of these plates already, but we have thousands of plates just taking up space, warehoused in Seattle and at the observatories. And so there's a lot further this program could go. Anyway. There are other interesting things people do with the plates. Here's some artwork made by the spouse of one of our engineers. And there's other pieces of art and furniture and office decoration. People have become very creative with these objects. They're really fun. So that's what we do. We get spectra. But more specifically, what do we do with those spectra? And so in SDSS-4, what we've been working on are 3 major programs. One is EBOS, which is a cosmology, large-scale structure program. One is Apogee, which is mapping the Milky Way. And one is MANGA, which is mapping nearby galaxies, understanding individual galaxies nearby. And I'll describe rapidly each of these programs. So this overall, we're actually now done with the observing. We started in the middle of 2014, and we completed last Thursday morning, I guess. And so this is this is actually an adjustment for all of us. We're no longer getting the emails every morning about how we did, and so I don't think we fully adjusted to the fact that we're actually done observing after 6.5 years. So EBOS is the cosmological program, and basically it's the culmination of 20 years of doing redshift surveys with the SDSS. And at the beginning of SDSS, if you look back at the project book, this is what the volume planned was. And then on the same scale, this is just a slice through EBOS showing, just sort of visually, we've actually measured a lot more effective volume, which is a technical large-scale structural term, a lot more effective volume than the original SDSS planned to, and we've gone to much more distant redshifts to measure large-scale structures. So this facility has turned out to be much more powerful than people originally envisioned it could be. Because not only did we just observe for 15 years longer than was planned, but we also used the spectrographs in different ways and upgraded them. So, and I'm going to focus on really just like one narrow slice of what eBOS has been able to do cosmologically, and that's the measurement of the expansion of the universe with the baryon acoustic oscillation. So the baryon acoustic oscillation is this feature in large-scale structure, which arises because early in the universe, if there's any dense spot, that dense spot is going to be high pressure, and a sound wave will be driven out from that location. Now that sound wave goes at close to the speed of light for about 400,000 years, but then it stalls. And then it stalls at just about the same redshift as the cosmic microwave background, as when the last scattering surface is. So if you observe the cosmic microwave background, you can very precisely measure the scale that this sound wave reaches. And it turns out, because you know the physics of hydrogen and stuff, baryon photon gases basically, because you know that, you can determine sort of in meters this length scale from the CMB observations. And this length scale imprints itself on large-scale structures. So if I look at the correlation function in large-scale structure, if I sit on a galaxy and ask the question, what's the probability above random of seeing some other galaxy some distance away from me, then galaxies like to be near each other. So the probability is high close by. There are declines as you get further away. And then there's a little bump, and this bump is associated with the same features that you see in the CMB. But you're measuring this in a redshift survey, so you're measuring this scale in a velocity units. So you measure this in kilometers per second. So you have it measured in kilometers per second, but from the CMB, you know what it is in meters or megaparsecs, and so you can determine the relationship between velocity and distance. And to get slightly technical, because you can measure this feature both along the line of sight and transverse to that, you can measure, if I have some sample at some redshift, I can measure both the Hubble constant at that redshift, or the Hubble parameter at that redshift, and the distance to that redshift. I can measure those two things independently. And with the SDSS surveys, eBOS, BOS, and the original SDSS, we can measure this at a bunch of different redshifts, up to redshift 2.5. And so if we look at these two different sorts of measurements, something like the expansion rate, something like the distance, this is what you get as those measurements. And shown in the curve is a very simple model. Your basic vanilla cosmological model, which has dark matter, which is slowing down the expansion, dark energy, or cosmological constant, which is speeding it up, and then you have some Hubble constant that you use as well. And so this, and these match pretty well, and these data points put very strong constraints on these parameters. But I think what's the most interesting thing that you're now able to do is, that's a very simple model. It just has those two components. But dark energy is, or a cosmological constant, is a very confusing physical thing to happen. Physicists, there are many different models for that, some of which end up being just like a pure cosmological constant, some of which vary from that. And we're interested in seeing if we can see any variation from that very, quote, simple model. We are also interested in seeing if, this number and this number add up to exactly 1, as it would in a perfectly flat universe, or if there's some curvature to the universe. And so if you want to ask those questions, you need the large-scale structure data in order to ask it. So for example, here's just a roundup of, if I take the cosmic microwave background data and say cosmological supernovae, I get these red contour constraints on these parameters. If I combine the CMB and the large scale structure data, I get these blue contours. If we combine all of this stuff, we get the gray contours. And so in order, if you want to look at a general set of cosmological models and you want to pin them down, you need to combine all of these data sets. You can't do it with any given data set on its own. And if you do that, you find that these models get pinned down very close to this simplest of all universes. And so that's one thing to take away from the current state of cosmology, is that this simplest model is surviving more and more stringent tests. Now, the other thing to take away is that there is one discrepancy which is very clear and remaining, and that's that any of these models predict a Hubble constant that you should observe locally, the local expansion rate. And they all the CMB combined with the BAO always brings you down to a low-ish Hubble constant, like 68 or 69. And when you observe the Hubble constant locally, you get something that's much higher. And this is the typically quoted result, although there's some variation among local results. But with the 95% contours, and you can see that there's a very strong, flirting with 5 sigma discrepancy between the cosmological, predictions of what you should see locally and what you actually do see locally. And so it's very interesting to take the constraints from cosmological models and ask, what can you do? Like, how can you play with a cosmological model to resolve this? And in terms of the physics of the expansion itself, it's very, very difficult to do that. And the reason is the large scale structure data pins you down so strongly that even when you allow for a curved universe and allow dark energy to evolve with time and to not be a cosmological constant, you still get very precise constraints on what the Hubble constant should be. And this discrepancy really survives. And so I think one of the contributions of the large-scale structure data is really nailing down this, even when you're allowing curvature or other complications, in fact. This is a very robust discrepancy to that. So that's sort of very briefly the legacy of eBOS, and of course I'm skipping over a lot more, but now I want to zoom down to much lower redshift to look at our own galaxy, the Milky Way. And these are observations that are done during bright time at both APO and Las Campanas Observatory. And so we have a map of our galaxy. We're here, the center's here. The red shows sort of where apogee should be able to see. And you can see, in all directions, because we have both hemispheres. And we're using infrared spectra so we can peer through the dust in the Milky Way disk. The spectra look like this. They're relatively high resolution. You can see all these features. This is a range of metallicities of stars, low metallicity stars with very few features, high metallicity stars with lots of features. And these features correspond to different elements. And so you can determine precisely, a whole bunch of different elements for each of these stars all over the Milky Way, and really look at its history and chemistry and dynamics, which is the subject of a lot of work, of course, that's going on here. And so, here's a simulated galaxy from Auriga that's kind of like the Milky Way. We would be here, and our questions are, There's a bar, there's a disk, there's some halo, a stellar halo around it. We want to really use apogee to untangle what's going on in the real universe so that people can ask the question, you know, how does this compare to what we predict? And there's a few really important tools that apogee uses. And the first one I'll mention is something that at the beginning of apogee was never anticipated, but that it's possible now for red giant stars to measure individual ages or constrain individual ages. And the reason for this has to do with the fact that there's something called dredge up, which changes the atmospheric abundances of red giant branch stars, and it changes it differently for stars of different masses. And because the mass of a red giant branch star is going to be closely related to its age, because it has to get to that phase. And so what that allows you to do is measure, in particular, this carbon to nitrogen ratio in a star and infer an age. And so, and this has been calibrated with, you know, astroseismological data and apogee spectra, and the contribution of Melissa Ness, who of course you all know, was being able to bootstrap this and apply it to just typical red giant branch stars in apogee, which allows you then to use it all over the galaxy. And so here's just a set of results showing the ages. These are median ages in bins of stars. And the axes, the vertical axis, well, let me start with the horizontal axis. Horizontal axis is just the amount of iron in the atmosphere of the star. And the vertical axis is the alpha abundance over iron. So alpha is like oxygen, neon, magnesium, these elements. And this varies in different stars because the gas that the stars formed from has been enriched differently depending on what happened before the star formed. And basically, high alpha means products of early enrichment. So if I have some star formation, it starts enriching the gas. Early on, the only thing enriching the gas is core collapse supernovae, because they go off very quickly. And they yield, you know, a lot of alpha elements relative to iron. And so that means that if I see a star here, it means it was enriched in some early phase of star formation. And correspondingly, you see that they are, in fact, the older stars. So far, so good. That makes sense. So Melissa used this a number of years ago now to make this map of the Milky Way coded by age, where the darker colors here are younger and the yellower colors here are older. And you see this inside-out growth of the galaxy, where the central parts of the galaxy and the galaxy disk formed earlier on average than the outer parts. And then there's an age gradient in galactic height as well. And this has been, you know, people have spent a lot of time untangling these observations. Here's just one example from Makareth showing just the profile of the old stars versus the young stars. So this is a very detailed picture of the buildup of stars in the Milky Way disk. Very, very potentially constraining observations. So that's one way to use the age. And then if we look at the alpha, sorry, I don't have a better version of this. I think it might be the highest resolution version of this particular panel. But if I look, you know, if I look at this alpha versus Fe, this is locally. This is basically near the sun. This is a diagram that's been known for a very long time. There's a sequence of these high alpha stars. There's a sequence of these low alpha stars. What apogee allows you to do is it allows this local measurement to be just one measurement in a whole panoply of measurements you can make across the Milky Way. You know, so each of these panels is sorted in radius in the galaxy as you go to the right, distance from the plane as you go up. And you can see some of the major features of our galaxy. So for example, this alpha enhanced population, this older population of stars, is much more prominent further away from the plane. This corresponds to what people call the thick disk. So this is sort of in some ways, a separate entity from the thin disk. That's a very controversial statement. I didn't mean to say that, but people treat it as separate. This high alpha population is also more populous as you go inward in the galaxy. And so again, you're getting this very detailed picture of where all the stars have ended up. And then you can combine the age, in this example, the ages and the abundances, and look at even more detailed questions. So for example, I can take the quote thin disk, the low alpha sequence of stars, and I can sort them by age. And then I can ask, for example, what is the vertical velocity dispersion of each of these populations of stars? That's related to how far away from the disk they get. The faster they're going, the puffier the disk that they form. And you get something which has been known for a long time, which is the age-velocity relation. But here, we're able to measure that age-velocity relation at different radii in the disk, showing it's different at different locations in the disk, and showing that the thick disk, or the high alpha sequence, obeys a similar relation, but just with higher sigma. So this is again, this is untangling this history in a very detailed way. And so some of these authors conclude that the Milky Way disk, for example, formed, quote, upside down, meaning that these stars have higher velocities because when 8 or 10 billion years ago, the disk itself was thicker and it's settled down. That's one interpretation of those. Again, I don't want to be controversial. But I think one of the most interesting things that's come out of apogee, when you think about these maps, is really showing the importance of what's called radial migration to the interpretation of these maps. So for a long time, when you thought about what happened to stars over the course of their lifetimes in a galaxy disk, you imagine that they're in roughly circular orbits. So you imagine they stay at roughly that same radius for their whole life after they form. But it turns out that theoretically, you don't actually expect that. You expect that spiral arms and the bars should be causing stars to migrate, like this blue and green curve, or at least this blue curve, over its lifetime, substantially in radius. So you expect radial migration of these stars. Typically, you expect them to stay in roughly circular orbits, but the size of that orbit changes over time. And that's something, it turns out, is necessary to have to understand the apogee observations. So the simplest, although in some ways easiest to slip out of, sign of this is that if I just say, look at the metallicity gradient of stars, the metallicity of stars as a function of radius, the youngest stars obey this fairly steep relation, which is typical of gas in galaxies. But the older stars have a much flatter relation, which can be explained. One explanation of that is that all stars, form from the gas, which always has this metallicity decline with radius. But then over time, if you mix the stars in radius, you will wash out that dependence.
Can I ask
Yeah.
something on this figure?
Yeah.
It seems that the error bars are strongly exaggerated, right?
The red, I believe, is the distribution. And so I think I don't think the red is reflecting the error bars. The error bars are the black, which are much, much smaller. I think the red is the variance in the distribution, not the error in the mean. I would say about 5% of all of our time on meetings is in projects like this is clarifying when we mean the variance and when we mean the error in the mean. It's very confusing, but I think I know that one. Another way of looking at this is, I'm going to skip because it's so complicated, except to say, no, you know what, I'm not going to skip. I'm going to do the following. If I look nearby in the inner parts of the galaxy, and I sort galaxies by their metallicity, I find something that I expect. So I have this measure of age, which is carbon over nitrogen, sorted from young to old. And the highest metallicity stars are the stars that formed the earliest. And so they're the latest, because they're forming from the most enriched gas, which is now. And so I have this distribution of ages, which is peaked at the young ages. As I go to lower iron abundance, I find older and older ages. That reflects what you expect, that the gas is building up in metallicity over time. So it's moving from these metallicities to higher metallicities over time. Whereas if you look further out in the galaxy, that relationship really goes away. And what you see is that the youngest stars here actually have this metallicity. And there's a bunch of higher metallicity stars that exist at that radius, sort of couldn't have formed at that radius. And also, they tend to be old. And there's really very little age metallicity relationship at this particular radius. And again, this indicates that there has to be something messing up that relationship, which radial migration is good at. And then finally, you can look at the metallicity distribution, again, as a function of radius. So here, sorry, I lost the labels, but this yellow curve here is the is the outermost radius, and the blue curve is the innermost radius. And the blue curve is sort of what you expect from some closed box model. You get this long tail, and this skewness you see in the blue is kind of what you expect from typical chemical evolution models. But this skewness goes away, and then actually the distribution becomes skewed the other direction. And models can actually reproduce this. So here's a model from Loebman. There's a set of sort of data-driven models from Frankel over the last few years. But they can only do this by introducing this radial migration effect. And what these models predict is that this radial migration, here's the solar radius, means that around the sun, about half of the stars came from several kiloparsecs away, a disk scale radius or two. So this is a key. So in terms of interpreting all of the previous plots I showed, sort of trying to untangle the disk, you need this radial migration in your model. And that, I think, has been one of the very interesting things to come out of Apogee. So I'm throwing away a lot about the bar, about the halo, about accretion. But I just want to give you a sense of the amount of information we now have about the history of the galaxy forming. But this is just one galaxy. And there are a bunch of other galaxies, which look really, a lot of them look really different. You have elliptical galaxies, we have smaller, irregular galaxies, we have galaxies without bars, we have different kinds of disk galaxies. There's a whole population of galaxies to explain. So we want to know something about those. And that's the subject of the last project in SDSS4 I'll talk about, which is MaNGA. And so MaNGA, basically, you take a galaxy. This is a nearby galaxy, like 100 megaparsecs away or so. And you, instead of putting one fiber on it, you put a whole bundle of fibers on it. You look at all the spectra from those fibers, and you can make a map of its dynamics, or its stellar populations, or its gas properties. And you can then interpret that in terms of its history of star formation, what its gas is doing, does it have an AGN? So you can sort of dissect this galaxy, not at the precision, you can dissect the apogee, but you get a whole bunch of different sorts of galaxies. So our aim in this project was to get 10,000 of these. And by the morning we ended, the morning of August 24th, we had gotten 10,010. So we stopped observing, declared success. And that was that. But there's lots of things you can do with these 10,010 galaxies. So one thing you can do is you can dynamically characterize them. So a good way of characterizing a galaxy is in terms of its angular momentum. So you have galaxies, and its angular momentum relative to like the mean angular momentum of a star. It's like the bulk angular momentum relative to sort of the average angular momentum of a star in the galaxy, which is this parameter here, lambda. And you have slow rotators where lambda is small. That's your typical massive elliptical galaxy. And you also have fast rotators, which include some ellipticals, also S0 galaxies, spiral galaxies. And this is an interesting classification of galaxies. So for example, I can plot this lambda versus the apparent ellipticity of the galaxy, which depends on the angle at which you observe it. And you see that spiral galaxies live up here at high angular momentum. These are the green points. And elliptical galaxies tend to live down here, although many of these blue points are elliptical galaxies as well. But this slow rotator population is what you think of as a classic giant elliptical. It's the textbook version. And then you can, with a sample like this, so this pattern has been known for 10 or 15 years, originally with the ATLAS project. But with a large sample, uniformly selected, you can start to ask questions like, how many massive galaxies are slow rotators? What fraction of them are slow rotators? And how does that depend on their environment? Because if they appear mostly in certain environments, that has an implication for the mechanisms that make their rotation slow. Like maybe then it becomes plausible to form them by many, many small minor mergers. And in fact, in the latest observations, this is what the latest analyses, this is what you see. You see that this fraction goes up with the density of the environment around the galaxy, the density of other galaxies around it, for the most massive systems. This is, again, still a controversial result. There's some, so you should look at this green paper and as well. But this is the sort of thing you can start to do with a really big sample of galaxies like this. You can also look at each galaxy a little more carefully and actually, instead of classifying the galaxy as a whole necessarily, you can split the galaxy into its bulge and disk components. And you can do that jointly with the photometry and with the MaNGA spectra. And so you can get a spectrum of the bulge part of the galaxy and a spectrum of the disk part, even in the places where those things overlap. You can separate the galaxies in this way and look at the components independently. And indeed, you can make one of these angular momentum diagrams for the disks and for the bulges. And you can see the dynamical differences between the bulge and the disk. So again, this is just another way of dissecting these galaxies. There's a really interesting way of doing this, which is you can specifically extract the dynamics of the young stars versus the old stars. You have enough information in many of these galaxies that I can get a rotation curve. This is the rotation as a function of position. So this is showing a rotating disk. This is just specifically the young stars in the stellar population. These are the old stars. And then this is the gas. Since the young stars presumably formed from the gas, you expect these two panels to be similar. But the old stellar population doesn't have to be the same, because it could have formed from the disk way in the past when the disk was, say, different. Or the old stars could have been perturbed. And in fact, in the Milky Way, you kind of expect something like that, because there's an age-velocity relation. And so you expect that the disk's dispersion and rotation should look different as a function of age. And so you can take Milky Way mass galaxies in MANGA, and you can look at this, what's called asymmetric drift. And what you find is that these blue points are the young stars, and what's shown is the difference between the gas and the star's circular velocity. And you see that the gas and the young stars always look similar, but the old stars are always rotating more slowly, or almost always rotating more slowly. But even for this narrow sample of kind of Milky Way-like systems, the amount of this asymmetric drift of the old stars relative to the young stars differs. And so whatever relationship exists in the Milky Way, whatever explains that, had better not do the same thing in every galaxy, because galaxies show a diversity of properties in terms of this age-velocity relationship of stars. So here you see, like, MANGA is then, taking this interpretation from the Milky Way observations and seeing whether it extends to the full population of galaxies. In this case, it doesn't. You can look at other things that are also similar to what you can ask with apogee. So you can look at inside-out growth in galaxies like the Milky Way or other types of galaxies in MANGA. So you can do a stellar population analysis of the MANGA spectra. And here's just a local galaxy. Here's the H-alpha emission. You see it slightly offset from the bar of this galaxy. And then if you look at the very young stars from this stellar population analysis, they follow the H-alpha, which is great, that's good. And then slightly older stars follow the bar. And then you can slice the history further back in time as well. So you can sort of time slice individual galaxies. And then you can take a bunch of those galaxies, sort them by mass. Red is the most massive sample, sort of Milky Way mass and above. And you can ask, well, what's the time in the past by which 95% of the stars were formed as a function of radius in the galaxy. So this is radius. This is a time scale for star formation. And what you see is that the stars are getting younger on average as you go further out in these disks. And that holds for Milky Way mass galaxies, but doesn't hold for lower mass galaxies. So this is similar to what Ness finds in apogee, but then what this is telling us is that for smaller galaxies, this effect isn't there. So that's inside-out growth. We can also look at the quenching of galaxies. So we can measure star formation from these spectra as a function of position in the galaxies. And this is, again, sorted by mass. Here it's this red is the most massive galaxies. And this is sort of your typical star-forming galaxies at each mass, and this is the profile of star formation. If we look at galaxies which have lower star formation rates, which I'm going to call quenching, sort of interpreting them as ending their star formation. Again, a little controversial, but bear with me. what you find is that, of course, they have lower star formation at all radii, but it's more lower in the inner parts of the galaxy than in the outer parts of the galaxy. So not only are the galaxies growing inside out, the inner parts form their stars earlier, but perhaps not surprisingly, they're also ending their star formation earlier. So you have this inside out quenching. And it's very important, I think, in studying this to distinguish between the growth versus the quenching. These are very different phenomena. So that's true for your typical quenching galaxy. But it turns out that one of the, and this is one of the powerful things about manga, is you can ask this question. Whether or not you have inside-out quenching appears to be a function of where that quenching galaxy is. If that quenching galaxy is isolated, or at least like not near a larger galaxy, that's what happens. It quenches inside out. Maybe that's some internal black hole driven process. Don't tell anybody I said that. But if you're a satellite galaxy, if you're orbiting some more massive galaxy, then your quenching isn't inside out. You quench the same way at all radii, which means it's some different thing that's going on. Maybe it's externally driven. So that's very interesting. And it's a question you can only ask with samples like this. So those things are sort of comparable to the questions you can ask with apogee of the Milky Way. There are a few other things you can ask with manga that is just about the gas in the galaxy, because all of these effects, the growth and star formation, the quenching, it's all sort of driven by the gas physics. And you can measure this in many cases directly with the optical spectra. So for example, you can see outflows of gas in galaxies. If you want to see ionized gas, you can look at the wings of the O1 emission, which you see a profile of that here for these particular galaxies. And you see these wings are indicating an outflow. And you can see that if you look at galaxies that have AGN in them, they tend to have the higher, the stronger outflows, although there are some star formation driven outflows as well. You can also see that outflow in the neutral gas with, say, sodium absorption and calcium absorption and some other tracers. But here shown in sodium. In this case, they actually calculate the mass loading factor of the neutral gas as a function of radius in the galaxy, and under a bunch of different assumptions, which sort of span the range of what you expect. But you can actually make these measurements with the spectra by looking at the absorption of the gas, obviously the stuff coming towards you. You can see inflow of gas. So the claim here, there's some warm ionized gas here in sort of a lump near this galaxy that looks like it's basically warm ionized gas that's flowing into the galaxy. It's also a bit of a controversial claim, but let's go with it here. Another thing you can see is you can see the effects of gas flow like that as it comes onto the disk. So this is an interesting set of observations where they look at galaxies and they find what they call anomalously low metallicity regions. So you have to figure out what you expect the metallicity to be, and then you look for gas metallicities that are much lower than that, and then you paint them blue in these diagrams on the right here. And then you can ask, okay, if they're anomalously low metallicity, maybe that's because it's pristine gas that's just flowed into the galaxy. Pristine gas is going to tend to come in with a constant nitrogen to oxygen ratio, because down at low metallicity, it tends to, it's what they call primary nitrogen, and so you get some fixed ratio between these two. But this ratio becomes a function of metallicity at higher metallicity when you get secondary nitrogen, where the amount of nitrogen you produce depends on your metallicity. And then in these regions, this nitrogen to oxygen ratio looks like it's a mixture of sort of the regular gas, on this nice blue sequence here, and the pristine gas, which you would see here at minus 1.4. And this anomalously low metallicity gas looks like it's a place where these two types of gas are mixing. More evidence this is really inflow. So again, this was a bit of a blitzkrieg, but I just wanted you to get a sense of the amount of different information you're getting from these surveys about our galaxy and about the population of galaxies. And despite having gone through this very quickly, there's a lot I couldn't say. I'm just going to have to skip, like measuring black hole masses for, quasars out to redshift 2, changing look quasars, a new stellar library for stellar population models. And, most of the stuff that's done here with Apogee, I totally skipped. Just ask the Apogee people here about that. So there's a lot I had to miss, and I would be a little remiss if I just didn't say what was coming after SDSS-4. It was actually very predictable what was going to happen after SDSS-4. It was SDSS-5, obviously. This is the director for SDSS-5 is Juna Kohlmeier. She spoke at this event not very long ago, so I won't repeat a lot of what she said, but they're looking at the Milky Way and ionized gas in the Milky Way with the local volume mapper. They're looking at quasars in the time domain with the black hole mapper, and they're really fleshing out our map of the Milky Way with the Milky Way mapper. And they are moving away from plates. They're using robots to robotically place the fibers in order to reduce the overheads between fields so that they can very rapidly observe in short exposures and cover lots and lots of sky. So I'm just going to leave up my summary and there.
Yeah. Thanks very much. You guys should just ask questions.
Yeah, I wonder if I can, there we go. Oh, there are a lot more people here than when I started. Well, I can, why do people keep ignoring the Friedman et al. And lensing measurements?
Oh, I was going to actually begin by first, congratulations. It's really wonderful to see the success of Sloan 4. Then an assertion, one shouldn't ignore Friedman et al. And the lensing measurements. It could be the Cepheid to go on saying it's 5 sigma. So that's just a statement. And then a question. Which is about these neat manga results on the bar with this age correlation. I'm trying to understand if this tells us that bars are long-lived, because it looks like these are correlations that if bars came and went, would go away. And something you mentioned that passing by, there's just so much great stuff here. Are you seeing these correlations in all the galaxies with bars or some of the galaxies?
You mean this time slicing?
Yeah.
You know what? So Petit they did this maybe with one galaxy, maybe a couple. They actually did not do a systematic look at all the bars. If you look at the Milky Way from the Bovie results from Apogee, it looks like the bars in solid body rotation, you expect it to be long-lived, and it's also old. So this may be something you see in barred galaxies where there's actually star formation going on in the bar. So there may be different sorts of bars that are occurring, but the short answer is there isn't a systematic look at this, I think, from the manga data at least.
Yeah, no, that'd be really cool because I think there are mechanisms where you'd imagine bars are stimulated by accretion events, and there's mechanisms where you think you get long-lived bars, and a systematic study of this in the manga data might be a way to reveal what's which mechanism is important and under which conditions.
Yeah, so yes, I agree. And people are looking at bars, but I don't think they've asked, I don't think they've asked this question. Most surprising thing? That's an interesting question. I actually think that the most surprising and useful thing was actually the ages. The fact that you could do, individual stellar ages and look at that. I would actually say that was the thing that would have been it was most impactful thing that wasn't anticipated, I think. There are other things that might have been more surprising, but less important. Adrian asks, what's next for me? Well, over the pandemic, I've grown my garden in my backyard quite a bit, and I've gotten very into that. So I'm very excited to spend more time there. I'm the director of the Center for Cosmology and Particle Physics, and so I'm going to be spending a lot more time locally. And actually, I'm kind of looking forward to just doing more science with the data we're producing, with the manga data in particular. So I'm actually not, I'm not personally looking for like another big project to do there. We just produced this huge data set, and I would really like to spend some time, helping to figure it out. Oh, Alberto has a question.
It's a long question, but I was very curious about the last bit that you showed with these potential gas inflows that you were identifying using the abundances.
Yes. So these papers definitely look at that question, and I think the answer is yes. Don't quote me, but I do think that these follow, in some sense follow the fundamental metallicity relation, in the sense that they are areas of higher star formation.
Yeah, so I was going to ask you that. So if you try to place them on the fundamental metallicity relation with the star formation rate, that's one of the factors. You see them there?
Yeah, I think that relation is followed locally. I think anyway. There's some papers by Sanchez's group from UNAM. There's a paper that's now a few years old from Guantan Zhu, who used to be here at NYU, and that asked that question very directly. And so I probably should be reminding myself what exactly those papers show. But I think that's right.